I'd like to welcome you to today's webinar. This webinar is part of our Scan to CAD to Print webinar series. Our topic today, product development with scan data, the complete process, how to create a part from scanning to 3D printing. My name is Robin Gonzalez, and in addition to being your host today, I manage the additive manufacturing sales for our strategic accounts here at Hawkridge Systems. Joining me today is an expert in 3D scanners and printers, Matthew Fisher and Jesse Hayworth from Hawkridge. For those of you new to Hawkridge, we've been providing engineering and manufacturing solutions to North American companies for over 20 years. As you can see, we have 21 offices and digital manufacturing labs across the country. In addition to products and services, we partner with the leading providers of engineering, manufacturing, and 3D printing solutions. So that is just a quick overview on Hawkridge. Now let's get into our topic today with Matthew and Jesse. I'm going to go ahead and pass this over to Matt, and he'll go ahead and take this into the next step.
Thank you for the introduction, Robin. My name is Matthew, and I am an application engineer here. And as Robin said, this topic is going to be about product development with scan data and kind of the overall complete process. A lot of times we have customers come up and ask, I have scan data, but I want to actually use it for product development, but I'm just having just the raw data. And what do I go from here? Well, hopefully in this webinar, we can shine a light on the complete workflow, just how you go from that scan data to your actual modeling process. And then what do you do after you have your modeling done? How do you clean up that model for printing, and then even what do you do once you have your print, so like an inspection step. So we're going to start off with just a quick little abstract about the case study itself, just the beginning to end, each individual step, kind of an explanation on what those steps are, what you would do during them. And then I'm actually going to go a little bit deeper into those individual steps. So I'm going to break down each one of those, the scanning process, the modeling process, how we go about cleaning that model, or I call it the STL, so that way it's ready for 3D printing, and then ending it off with like an inspection of that case. I'm only briefly going to talk about the 3D printing side because Jesse is going to jump in afterwards and talk a lot more about the 3D printing, what we went into prototyping it, how we can improve our print, so that way we can get the best model with our data. And we're gonna have a little Q&A at the end. I wanted to just throw out that this is a pretty big topic. It's something that we can't really cover completely in an hour. So we're having a couple of different webinars following up each week this month. So the next one is going to be about master modeling. So how do we use scan data to create multiple parts? And then how do we organize all these parts? We're gonna have one about revolutionizing with 3D with rapid prototyping. So it's kind of be, it's almost like a part 2 to this. So we're gonna use the same kind of case study, but we're gonna explain about how we can model something differently with scan data, not just within Solidworks, and then kind of what goes into making the best prints. Again, how do we optimize our prints so we can get the most out of it, or even reduce our cost and time? And then the last topic, we'll be using scan data for marketing. So how do we use scan data for renders and our websites, and show our customers what our product would be without actually even manufacturing it, using our scan data, or maybe we can make a custom design and send a preview to them, as well as using scan data for simulation. So it's a topic that not a lot of people think about, but it's actually a pretty big one with scan data. So for the workflow, this isn't anything abnormal compared to a normal workflow with working with scan data. Typically, we will always start off with scanning that object, and we're going to get that raw data, and then we have to process that data. So, this is one of the steps where a lot of people will hire someone to get maybe like a laser scan, and they have this raw data, and they don't have really anything to work with. Well, that's because you have to process it first. Once we finish processing that data, we can get something like a mesh. Now, mesh does have some properties to it, but it is pretty graphical. It doesn't have that much actual modeling properties to it. It's not an actual solid yet. While we can do a lot with meshes now in SOLIDWORKS 2020, for example, it's still really handy to have that as a actual solid body, so we can use it with our other future parts in being able to subtract them with like Boolean operations with one another. So that's why after we've imported in that process data into our modeling software, we're going to create our reference bodies. And then once we have these reference bodies, so turning our mesh into something usable, we're going to actually begin designing our phone case. And this is really where a lot of the manual work comes in. I know this is kind of step 5 in the process of this workflow, but in actuality, a lot of the scanning stuff, we get that scan data, but the processing of it, importing it into the software and creating our reference bodies can actually be pretty quick. We haven't really done so much engineering work just yet. It's not until we get to that designing of the case yet, where we actually start applying our modeling practices. once we have our case designed, we can export it out. So I'm going to export it out and as an STL. And while we could send that right to a 3D printer, because we're working with scan data, a lot of times we have to do a little bit of cleaning up. Maybe we have to smooth out some edges. We have a couple of bumps that we don't want. So we go through and clean up that exported body, which we then send to our printer so we can get that really good high quality print. Once we have that print, this isn't a step that's really needed when you're working with 3D printed parts. However, if this was a complete case study, and let's say you happen to mill this instead or weld it together, a lot of times you want to inspect that final part. So we're going to actually use our 3D scanners again to scan our finished product and then compare it to what our model was and within SolidWorks, so we can just see just the deviation report with that. So in case we do need to actually improve our print, in case we actually do have any kind of defaults, we'd be able, or defects, we'd be able to see that and clean it up for our next product. So that is the workflow, but how about breaking this down into individual steps and actually talking a little bit more about that? So step one is scanning the phone itself. I used the Artex Space Spider. It's a really handy handheld scanner. It's a structured light scanner, so it's projecting a grid onto our object, and the defects in the grid is what we actually gather our data from. And the Artex Space Spider is really handy. It's a very fast scanner, and it gets really high level resolution. So maybe we don't need 0.5 millimeter resolution for something like a phone, but we were able to really define where those button locations are, which is what we're really after. And it's really handy for scanning small objects. Like I said, this is a built for really hand-sized objects, and smaller. It can go a little bit bigger, but really shines with something like a phone. And it was also really quick to do. So a lot of times with scanners, you might have to set it up and process it all together. Well, I only needed 3 scans to be able to complete this object. I needed one on the front, back, and then one on the side, which I'll explain about in just a moment. So as for the scanning process, I use something like the A-sub spray. Because this is a structured light scanner, we would want to really use a disappearing spray, so we can add some opaqueness to the object. Because this is a dark object, that's where structured lights kind of have trouble with. So adding some kind of spray that would disappear on its own, I mean, this is my own personal phone, I don't want to ruin it, so this disappearing spray leaves itself after an hour, perfectly usable afterwards, so it was really good for that. As I mentioned, I did 3 scans. So one was on the front side of the phone, one was on the back, and then I did one in the middle. And why we do these middle scans is because we have thin object. The phone is pretty thin. We need something to kind of piece everything together. And having a high quality, good scan is really, it's the framework. It's going to be the bones of everything after this. We want to make sure that we're not cutting any corners. We want to make sure that the thickness is proper on this phone. Having an extra 30 seconds to get that side scan so I can piece things together just makes all the future processes better. And I did process this in Arctic Studio 14 at 0.2 millimeter resolution, so we can see down to 0.2 millimeters on detail of this phone. Again, it's pretty high for what the phone is, but because this is a very smooth shape and I really wanted to get those button outlines, this was perfect for the situation. And Arctic Studio is now at 15, so this process actually could be even quicker because the newer version has improvements to the meshing part of it. So we now have our raw data and we've converted it into our mesh. So now we're on that third step and bringing it into our software. So as a mesh file, it's just saved as an STL. I export it out, it's still in the same 3D space so I can align it within the meshing software and bring it into SolidWorks. I'm using Geomagic for SolidWorks. This is an add-in within SolidWorks that allows us to really use mesh data. So you might have previously used within SolidWorks Scan to 3D. This is a really handy tool with being able to manipulate meshes and turning them into solids. However, add-ins like Geomagic for SolidWorks add a little bit of extra detail to the ability of what we can edit with a mesh. It treats it like a body inside of SolidWorks instead of just graphical data. I can do something like auto surface, which is actually what I am going to use on the on the phone body or the mesh to create my solid body and reference bodies. And auto surface is just a quick way to do a one-to-one conversion of mesh to solid information. And again, that solid information is what we actually can interact with other solid bodies. Mesh, not so much. The solid gives us a little bit of extra ability to manipulate. And this is all done right within SolidWorks because this is an add-in. So if you are used to the SolidWorks workspace, once we have our solid body, it's going to pretty much just be the same workflow that we normally would work with modeling with any other solid. So just a quick rundown of the overall process. We input in our mesh. This is from the top left, and then we convert it into a solid with that auto surface. So as you can see, we now have this kind of gray body. This is a solid information instead of just graphical information. I went about modeling button locations. So, where my camera is, where my power button and the volume button are, I want those outlined so I can create this reference body. Um, and with this reference body, I can insert it into any other part that I want. So let's say I'm not even just making a phone case. Maybe I want to make a charger for this, or I want something to connect to this phone at a certain spot. Well, that's where these reference bodies come in. And it's actually going to be a topic again that we're going to be talking about in the future webinars regarding master modeling. But for this webinar, I wanted to actually show this workflow because it sounds like, it sounds like it's a little bit too easy. It sounds too good to be true, being able to just convert that mesh into a solid. But actually, it's a pretty straightforward process. So with that, I'm going to send it over to Solidworks. And in here, I'm just going to go over just that workflow. So first off, I'm going to go over to import and select on my STL in my workspace. Within the Geomagic for SolidWorks add-in, we have several other tools available. So once this comes in, you can see that we can actually do other kind of manipulations on this mesh. So if I need to reduce it any further, I can do that, or I can do something like a repair, which can go through and see if there's any kind of sharp edges on our mesh, any kind of non-manifold sections, and so on, and repair that so that way we have a better quality mesh to work with. Again, these meshes are the skeletons of all of our future steps. So we want to make sure that they're really proper so we don't have any hiccups down the line. What these kind of non-manifold sections mean and these small hole components, you think, well, if it's graphical data, what actually is happening? Deep down, meshes are actually a series of triangles, and you have to think of these triangles almost as if they're their own surface. So it's a little bit abstract to think about that at first, but once you understand how they can fold into one another, you can see how there can be hiccups down the line, especially with working with certain types of scan data. But with that, the repair is complete. So I can now go over into something like auto surface, which is going to do that one-to-one conversion. I'm going to select my geometry type as organic. Organic just means that this isn't something with sharp edges. This is a very it's almost as if it was a hand carved phone because it has all these smooth edges and transitions. So it's a very organic shape. I'm going to have my patch estimate count as auto, and I'm just going to click OK. And what auto surface is doing is, I just mentioned how the mesh is made of a series of triangles, or sorry, a series of surfaces that are triangles. What auto surface is doing is laying down a series of spline lines over this mesh to create its own patch called NURB surfaces. And NURB surfaces are just a series of smaller square sections. These spline lines lay out and create a bunch of squares, and then these squares are converted into surfaces, and as if it was saran wrapped onto our mesh. They're gonna find all the little bumps and defects and turn that into a solid as well. That's again this one-to-one conversion. And what auto surface is really handy for is if you just need to create a reference body, or let's say you have a section of a part that you just cannot model. Let's say you're working with human factors and you have a hand and you just can't model all those little details, but you need to insert a very precise spot onto that freeform shape. Well, what auto surface will allow us to do is convert it into that solid, and then we can add in these prismatic features afterwards. It's a method we call hybrid modeling. It's a really, really handy tool, and really where scan data kind of benefits from is being able to take those sections that you just cannot model. It's too organic, it's too freeform, or you just need something that just uses as a reference, and you can just convert it into a solid with something like auto surface. There are other tools such as cross-section. Cross-section will allow us to be able to take a cutting plane and cut into our mesh, creating some reference spline lines. So if we really wanted to draw in ourselves, we can do that. But in this case, we just need the reference body because I'm going to be inserting in button locations afterwards. So auto surface works just as well. And it looks like the command just finished. So if I hide my mesh, it's treated as a surface body, I have this remaining solid. And if I actually show my edges, you can see the NURB surfaces laid out throughout this. So every single one of these lines is that spline line that the add-in went through and found on its own, and then stitched them together to create this solid body. And again, we are working right within SolidWorks. So as we're all very familiar with, I can just go right into the sketching tools and just treat this like a solid body. So I can go in here, maybe I want to outline some of my button locations. So I'm holding down Control right now so I don't snap to any of those points. But here we go. Sketch right in here and then extrude this out. And if I merge them together, it creates a single solid body. And now we're just building up our reference body. So I can go through and find the other locations on this. Again, I've already aligned this to a global origin inside of my meshing software. We could do this inside of the add-in as well, but it's oftentimes best to manipulate the mesh inside of mesh software if you have that capability, which I did. So I did all the alignments inside of Artex Studio. So I'm just going to continue extruding out, just outlining the extra button locations so we have something a little bit more workable with. Again, turning that scan data into something that actually is usable, the big question that a lot of people ask. Just gonna add one more button location. And then if I extrude this out, we now have all of our buttons outlined and we have that reference body. So now we're done with our next step of this modeling process. So we've done our scan, we've converted it into our mesh, brought it into our modeling software, and now we have our reference bodies. And at this point, a lot of times this is kind of what a lot of people are looking for, is this reference body, something that they can now insert into other parts. So if I save this and I can go in and start a new part, I can insert this in, and this is kind of what I did. Like I said, I did a Boolean cut. So using multiple solid bodies, we can quickly extract another solid body out. So insert part, and it's gonna pop up with that phone that I just saved out in the same origin. Different units. What that warning was saying is that the units might be different. While my template is different between the two that I just created, something that you have to remember is mesh data is unitless. So again, while we're already talking about complex topics with the triangles being like a surface, well, if you export out a mesh, it might be 5 by 12. But what is that 5 by 12? Is it 5 by 12 inches? Is it millimeters? So that's kind of what you have to, depending on what you bring it in, that's what really assigns the units to our mesh data. But in our case, we have our phone right inside of here. And now just what I can do is set up a new sketch. And this is how I went about making that actual phone. So again, the actual design work. So we have our reference body. I can now sketch out an outline for my phone case. So I can do both sides just to make sure it's completely encapsulated. If I want to have a thicker bottom side to the phone case, I can do that. I can click OK. As you actually see, I only have one solid body. Well, this is because I actually merged them together on accident. So if I just go back and edit my tool, I can say unmerge those results. And we have our two different bodies, and I can do something like the combine. So if I want to go through and subtract from one another, I can do that. So you see this is now a hollow body. I deleted the reference body from my actual model. I can go a little step further. I'm going to do offset entities, reverse these, and set a 2 millimeter parameter, just so that way if I happen to adjust the outside phone case, everything will be adjusted as well, making that kind of smart modeling, that designed with intent model. And I can go through and just top this off with an extruded cut. And we have a base of our phone case, so I can go a little bit further. I didn't delete the backside, or I didn't add a back side of this, so I can go through, edit up my model if I want. So if I go through and select this one side, I can go through and highlight this section and extrude this out, just defining where maybe something like my camera would be. And now with this new added feature, if I go back over into my part that I just created of the phone case, it's dynamic. It's because it's referencing that reference body. That the phone is essentially the master model to this sub part. So we can really have a lot of editing features to that. And again, just being able to just take a scan and bring it into Solidworks, and then just doing that one-to-one conversion so I have something to work with just goes a long way with being able to, instead of having to create a bunch of spline lines and maybe I have to make this phone exact or another kind of part exact, just being able to do that conversion really helps out. And we have a good base, and I went through further at this point. This is kind of going to be like in the cooking shows, I throw the turkey in the oven and it comes out correct. But as you can see in the feature tree, I really just added a couple of fillets to this end product, and we have our finished phone. So with this, our modeling is done, and now we can actually move on to the printing side. So now we're going to move on to the next step. So going back over into our slideshow, step 3, cleaning our STL. So you might have noticed on the bottom side of our phone that we had a couple of those NURB surfaces still showing. And while that is good because that means that we have the smoothness being defined within our phone case, we might have little bumps here and there that we don't want. While this phone case might have been very smooth, this is a situation that we're trying to apply to everything. So what if you have a rusted pipe that you're fitting things to? We don't want that rust to show up in your model. We're going to want to clean that up. So I'm using Geomagic Wrap. It's a mesh manipulation software. So it allows me to bring in different types of meshes and different types of files into there and edit it up, making it a little bit cleaner for printing. And in fact, actually, Jesse's going to show a little bit about why we went about this and the difference that it took or the difference that it made with our print. On the left side of the screen, we have the exported mesh directly from Solidworks, and you can see it's not the cleanest looking object. It's got a couple of spiked points because of where we defined some of those button locations. As you can see, it's got almost what looks to be fingerprints and smudges from the scan itself that it picked up. And I went through and ran it through this through a smoothing tool, and I did another mesh doctor because again, we're working with new STL data, new kind of sharp surface points. So I want to make sure everything was perfect, ran it through the mesh doctor, and then I even smoothed out the bottom side. And that smoothing out, as you can see, adds just a lot of cleanness to the phone case, makes it a very nice clean product. And there we go. From that, we were able to make our first prototype. So I sent it over to Jesse. Jesse put it on our Mark Forged, and we printed it out same day. At this point, again, we're talking about a lot of topics. I would say by this time, it's only been about an hour and a half into the actual beginning of the process because scanning doesn't take that long. That actual modeling, as you saw, doesn't take too long. So we have the same day prototype coming out with going from that scan data even to our finished product. We have the second view, and I actually even have it right here, and it fits really well into my phone. Well, this is another version of it that we printed. This one works pretty well with the phone. I'm able to slide it in, and it works really nicely. So we have our print, and then now, just like I stated, if this is a typical product development, we want to go through some kind of deviation report, some kind of quality control. So that's where something like Control X can come in handy. Control X allows you to create in-depth inspection reports pretty quickly. In this case, I only needed to click 3 buttons before I can get that 3D color map, just because I needed to just align my data together and then actually generate the color map. So we can import in various types of data into here. In this case, I actually use the hexagon absolute arm to rescan the phone case. It's a laser scanner. So again, we're now not even using structured light scanner. We're using a laser scanner, getting that real raw point data and converting it into a mesh again. So we scan our phone case, convert it into a mesh within something like PCDMIS, the hexagon software, and then we were able to export that STL out and bring it into Control X. Geometric Control X allows you to directly import in from SOLIDWORKS parts. So we didn't even have to export out that part file again. We can actually go right from that SOLIDWORKS part into Control X, taking the STL and bringing it in as well, so we can have these multiple file types within the software. I did a manual alignment, and then after the manual alignment, I did a refined alignment or a best fit, so that way they can line up pretty well. And I actually I get a little histogram showing just how well they are aligned. So if I see that this is really skewed to one side or another, I'm first going to go through that color map just to see if really it is an issue with possibly the part, or maybe I can improve that alignment. Maybe I can use like a datum alignment if that's required, or a specific point alignment, defining certain features and aligning based off of those. As for the color map, I did set it to about a 0.5 millimeter tolerance. So this is a pretty good quality tolerance just because I want to get an overall idea. I wanted to see if maybe something with the print might have had a hiccup. I wanted that direct feedback so I can tell Jesse, hey, maybe we need to go through and fix this section on the part, or maybe we need to fix this up in the print. That's all doable really quick and noticeable. Can even define certain sections. So let's say, with that back corner with the blue area, my deviation is off by a little bit, I can outline it and then send that into my report so people can see that. And that's really the overall workflow. So we go from the scan data, we capture our product, we digitize it into raw point data, we convert it into a mesh, so something that we can now actually bring into other softwares and start working a little bit better with. We take that mesh, convert it into a solid for our reference bodies. Now we have this solid body we can interact with other solid bodies with. We actually designed our phone case, so I actually put in our engineering caps and built our product. And then we went through and cleaned it up a little bit further just because, again, sometimes we have little areas that we want to improve upon. Maybe we don't need to have all these little bumps. We want to get a really smooth surface, so we can clean that up within Geomagic Wrap or other kind of smoothing meshing software. And then at that point, we print it, and then we can do our inspection. And again, this is all in about the span of a day. So we get that print, same day, found out that there was an issue. We made the adjustment in our SolidWorks part, and then send it back to the printer. And again, Jesse's going to kind of talk about this a little bit more. And with that, I'm actually going to send it over to Jesse. That is the end of kind of the product line. Like I said, I briefly talked about the printing side, but Jesse will now talk a little bit more about what actually went into our print and what we went about with reverse engineering and optimizing it. So with Jesse, if you want to take it away.
Hey, Matt, thanks for the introduction. Like Matt mentioned, my name is Jesse, and again, I'll be covering a bit on what went into creating the physical prototypes for these phone case iterations and how we kind of decided what changes we needed to make. So for this particular set of first phone cases, we used our Markforged printers, which you can see two of on the screen at the moment. Markforged printers create parts using a process called fused filament fabrication, and what that basically means is that a print head extrudes a bead of material and builds up geometry layer by layer until the geometry is finished. The main material that Markforged uses is called onyx, which is a nylon material that contains chopped carbon fiber inside of it. A lot of the Markforged printers can also inlay continuous strands of fibers like carbon fiber or Kevlar into parts, which will really greatly enhance the properties and performance of a print. These materials let us create strong in-use parts basically right off the print bed. Markforged also uses their own software called Eiger to prepare files for printing, which I'll cover here in a bit. Eiger will accept STL files, like Matt mentioned, which makes it pretty CAD neutral, and it's perfect for bringing in a processed scan file. So here we have an animated example of bringing the first phone case into Eiger. Orienting a part in Eiger is super easy, and all you really have to do is mouse over a surface, which will highlight it blue. If you click on a highlighted surface, the software will place that surface directly onto the print bed or parallel to the print bed if other geometry prevents it from being placed directly on the print bed. Now, Eiger is what's known as a slicer, which means, again, that it converts or slices STL files into those extremely small layers that I talked about. These printers will, again, create parts layer by layer until their geometry is finished. The slicing is all automatic. There's no manual tool pathing of all the different layers. And for a part like this, it really only takes a few seconds to process. Now, when a part is sliced, Eiger lets you see the tool path for each layer that will be created by the printer if you want. This is really, really useful for confirming whether or not something will print well. Inspecting a part is also really, really easy. So if you see on the bottom left, we have our display of the current layer out of how many layers of the part, and the total height of the part at the current layer we have selected is on the bottom right. So how do we make use of any of this? Well, for the first phone case version, we brought it into Eiger, sliced it, and then took a look at some of the layers on the internal surface. As you can see on the edges of some of these layers near the center of our case, there are a few artifacts that come from the uneven surfaces on the phone that the scanner picked up. Now, none of these are really very extreme because, like you can see on the lower right-hand number, as we're sliding through the layers, the highest deviation is only about 1 millimeter. So it's not really going to have a big impact on part performance. So for the aesthetic purposes only, Matt and I talked it over, and he ran some of the smoothing methods that he went over here just a few minutes ago. And here's a result kind of again in the internal view of the first pass that Matt was able to make. And you can really see the difference between the two. So on the left, we have a layer from our first version. And on the right, we have a comparison layer from the second smooth version. This first pass really helped to remove some of the artifacts. So that was the first prototype we went with. And just to bring it up again, here's a quick snapshot of the first completed print of our phone case prototype on a Mark II. We'll move for a closer look now. And as you can see, the surface finish of the case is really great. We do have some layer lines on the inside of the part, again, due to how our slicer prepares files for printing and the height deviation of the phone. But like I touched on earlier, this won't really impact part performance. So with our first prototype iterated and again printed in less than a day, the next step was obviously to try it out with the phone. Now, I did mention earlier that Onyx is a nylon-based material with some chopped carbon fiber inside of it. So even without continuous fiber strands, it's already really stiff. This actually proved to be a bit of an issue with the first design of the case, as the internal fillets of the prototype didn't really allow for enough flexibility to get the phone inside without risk of damage. So since this was just a prototype, we cut off the top side of the case to test a little bit of the fit without risking any of the damage, to see if the overall kind of idea of the design was right. So the problem with the first prototype meant that we could proceed with two potential solutions. The first was going to be to take our previous physical cut of the phone case and bring that idea back into our design, removing part of the geometry from the case. This ended up being kind of an unintended but really good example of the idea of rapid prototyping with 3D printing. So getting Matt the first physical version within a day allowed him to test some fit and make some changes to the file. With those changes, we then got the modified file from him and quickly started to test the next version. So the second potential solution without changing materials was going to be to modify our print settings instead of the file itself. To save on print time and material cost, 3D printers will typically create a partially sparse interior, which will still give strength while reducing weight as well for the entire part. For Markforged systems, the default infill shape is a triangular infill, which is really good for stiffness, but not so much for flexibility. So to try the first phone case again without modifying geometry, we could go into our print settings and easily swap to another infill type. Instead of triangular fill, we can switch to a hexagonal fill, which is more sparse and can give geometry more flexibility. So kind of just a more of a representation of an idea how this can change parts. Here's a direct comparison between the same layer with the two different infill options. The one on the left is that default triangular fill that I mentioned, and the one on the right is our hexagonal fill. Each of these lines in the central area of our part represent a solid wall of plastic, so you can really see how the hexagonal fill opens up space of the part. And just like I mentioned earlier, this is all really, really simple. It does involve reslicing the part, but again, that's more of a few seconds versus an entire workflow. And just like with the first version of our part, here's a picture that shows our next two prototypes. Now, the one on the left is a hexagonal fill, and you obviously can't see that since it's on the inside of the part, but we figured we'd include the two cases here anyway. So at that point, we have gone through several prototypes of our part, but what about maybe sprucing it up a bit and maybe getting a larger number of parts out the door? Well, to do that, we took one of the phone cases and modified it with some color with the intention of printing it on one of our HP Multi-Jet Fusion 580 systems. These are powder bed based machines, and they're really meant to get a lot of parts out the door quickly, and the 580 specifically can print in full color. So because of the geometry of our case, applying color to the STL was really simple. Like Matt did earlier, we imported our geometry into Solidworks as a solid body so that the surface could be modified. Once we did that, we used a sketch block of the Hawkridge Systems logo to create a split line on the back surface. Separating the logo from our case with that split line let us apply a white appearance to the whole phone case and a blue appearance to the Hawk itself. Now, HP printers can be a bit different from Markforged printers since they can recognize multiple file types. They can also accept STLs, but an STL wouldn't really let us retain the color easily. So to keep the color in our design, we exported the phone case as a 3MF file, which lets us keep that color. Before bringing the case into the HP printing software and actually printing it, we used the 3D Builder app that's built into Windows 10 to really quickly verify that the color and geometry were present with no errors, and everything looked great for our first pass, so we forwarded it to the printer. When the print was done, all we needed to do was unpack our finished phone case from the HP build unit. Like I touched on real briefly earlier, these are powder-based systems, and they're really meant to get a lot of volume of parts out the door quickly. As you can see, this color prototype turned out really well, and if it meets our needs, we can use this to kind of move into production and print a lot of them. So that was kind of a really quick overview, and that about covers it for the 3D printing side of things that we did for this case. I think this whole phone case example really shows how 3D scanning and 3D printing opens up the door for reverse engineering and rapid iterations. Obviously, the part itself was fairly straightforward, but for things like producing parts that aren't made anymore, or for converting your physical inventory into a digital one, this combo can be really, really great. And with that, I'll throw it back to Matt.
Thank you, Jesse. And yeah, thank you so much for going more in depth about that printing side of it, and kind of just building off of what you were saying a little bit early, just a moment ago, about how being able to reverse engineer, being able to remake parts that don't exist, or being able to just combine the two, and getting that same day prototype out is just really that kind of bridge between working with the physical objects over to the scanning objects. It really helps out with just being able to really expand upon these different different ideas, and we can really go and extrapolate from here. So again, this is a pretty simple case, using a phone for a future product, just designing a case around a phone. But again, we can scan something like a pipe, or we can scan something like an arm or a hand, and model around that within something like Geomagic for SolidWorks add-in and SolidWorks itself.
Once again, everybody in attendance, I appreciate you for being here today, and we hope that you will join us next week for our next webinar session. Thanks again. Talk to you soon, everybody.